Nucleophilic substitution reactions of alkyl halide. Now, alkyl halides show the different types of reaction, one of which is nucleophilic substitution reaction. First, what nucleophile is. So, nucleophiles are the molecules or ions with a free pair of electrons, or they have at least one pi bond, can act as a nucleophile. So nucleophile basically donates electrons. They are Lewis bases. A nucleophile is a chemical species that donates an electron pair to form a chemical bond in relation to a reaction. But what about the nucleophilic substitution reaction of alkyl halides? So in these reactions, in which the halogen of an alkyl halide is replaced by a nucleophile, or they are defined as the substitution reaction, in which the nucleophile, which is mostly a negative ion, displaces the halogen atom from alkyl halide. So nucleophilic substitution reactions are of two types. One is Sn2 and other one is Sn1. So basically this Sn2, which means the nucleophilic substitution bimolecular, and Sn1 that is for unimolecular. We'll discuss it. First, let us see its reaction type, how it is happening. So in this reaction, the nucleophile, basically nucleophile is represented with this Nu nucleophile with the pair of an electron. It will attack on this substrate molecule. Substrate is your alkyl halide. Alkyl halide, this carbon, the central carbon atom, which is partially positively charged and partially negative, this halogen atom. So in this, halogen is displaced by this when this nucleophile uses its lone pair of electrons. This results in the substitution following the attack. So this new compound is formed, which is with this nucleophile, and halide is coming out as a leaving group. So this is general form of this reaction, nucleophile, which is attacking a substrate molecule, and the product form, it depends upon the nature of the nucleophile which is attacking. So different products are being synthesized by this type, this nucleophilic substitution reaction. This halogen is coming as a leaving group, leaves behind as a leaving group. Okay, now so here reagents in nucleophilic substitution reaction is used aqueous sodium hydroxide or potassium hydroxide. Sometimes the solvent is necessary in case of Sn1 reaction, and product from its hydroxide is used, then that is the alcohol, nucleophile OH. Look at this equation where the ethyl bromide is reacting with sodium hydroxide. So it displaces this bromide ion and giving you alcohol as a product, and sodium bromide as a side product, which is formed by reacting this leaving group. Bromine is reacting with the sodium, it will give you this. Now nucleophilic substitution reaction bimolecular, Sn2. So 2 basically is for bimolecular because the two species are involved in the rate determining step, and Sn for substitution, and is for nucleophile. So here you may see in case of Sn2 what conditions are necessary. Keep in mind that this nucleophile attacks the nucleophile attacks the halide carbon only from the back side. Here the complete inversion takes place, no side reaction occurs, and solvent of low polarity favors this reaction. It follows the second order kinetics. So steric factor also influence the rate of reaction. So here what is happening, look at this reaction, this alcohol which is reacting with this alkyl halide. So what happened in it, this alcohol is attacking from the back side, and this situation is formed where this C formation of COH bond is happening, and CBr bond cleavage occurs simultaneously. In this state, what happened? This is the transition state, in which the it possesses the maximum energy, and where one bond is on formation and the other bond is on cleavage. So here simultaneously a state is reached between the reactant and the product, and this state is known as the transition state or activated complex because it possesses maximum energy. So for some time this stage is reached when both OH and Br ions are partially bonded to the halide carbon. This one, this state is known as transition state. So new bond which is going to be formed is COH. This is in formation, and this bond is in breaking process, CBr. So this is the slow state and is rate determining step of the reaction here. So in the course of the reaction, configuration of carbon is inverted. So the rate depends upon both the concentration of OH, means this nucleophile, and the substrate molecule, which is alkyl halide. And that's why it is known as your Sn2, because in the rate determining step, these two species are involved. So this is the two second order kinetics involved. So what happened in after this transition is a product form which is alcohol. So OH is directly bonded to this carbon, and which is giving you the alcohol as a product, and this Br takes away this bonding pair of electron, and bromide ion is your leaving group. So this Sn2 reaction mostly here occurs with the primary haloalkane. So this undergoes because of these primary alkyl halide favors this Sn2 mechanism as compared to the secondary and or tertiary. So this is just this reaction takes place in one step, but two substrate molecules, two reactants, one is nucleophile, other is substrate, is involved in rate determining steps. So the product form is alcohol. So basically Sn2 nucleophilic substitution reaction occurs in one step process. Look at this reaction like transition state, where this is the reaction coordinate. This is showing the energy when these both the nucleophile and substrate molecule, this is methyl iodide reacting. So what happened in it? A state is reached where it possesses the maximum energy, and this state is known as transition state, where OH is attacking from the backside, and this halogen, which is iodide ion, is leaving as a leaving group. So this state is basically a transition state, and it possesses the maximum energy. So here it is possesses the highest energy. So when it lowers down its energy, it gives you the product, desired product, because OH is used, so it will gives you the alcohol, which is your methyl alcohol. So let's look at the mechanism or the reaction of Sn1. So in nucleophilic substitution reaction, unimolecular reaction, which is your Sn1. So in this reaction, the rate depends only on one reactant molecule, which is your substrate, but not as a nucleophile, because it is a two-step process. First, the molecule is split into negative and positive ion. First, this dissociation of this bond takes place. The CBr bond takes place, and here the polar solvent favors this reaction to dissociate this bond, and after splitting, the nucleophile then attacks in the second step the carbonium ion to form the final product. So after the dissociation of this, first step is dissociation, and it will gives you this carbonium ion because it takes away bonding pair towards the bromide ion separates out, and this becomes the carbonium ion. So carbonium ion, once formed, is then attacked by a nucleophile to give you the desired product. So its rate determining steps is only one, where only one substrate molecules is involved. So here this Sn1 reaction is unimolecular. So the nucleophile can attack the halide carbon from either side, because first the carbonium ion is formed, partial racemization takes place, solvent of high polarity favor these reactions, and it follows this first order kinetics because only one species, which is substrate molecules, is involved in rate determining step. Tertiary alkyl halide generally reacts by Sn1 mechanism. Now look at this unimolecular energy wise patterns of what is happening. These are the reaction coordinates where alkyl halide reacting with the nucleophile. First, the dissociation of this bond takes place, for it is basically maximum energy, then lower down here. Lower down the energy graph, and this carbonium ion then attacked by a nucleophile to gives you the products instantly, and then halide is leaving behind as an. Now here is some of the comparison between Sn1 and Sn2. So rate totally depends on this substrate molecules. That's why it is first order kinetics, and here the two substrate and nucleophile is involved in rate determining steps. So this is nucleophilic substitution by molecular. Carbocations form in case of Sn1, but there is no formation of carbocations. It is two-step process. First is the formation of carbonium ion, and then in second step nucleophile attacks and gives you the desired product, while in case of Sn2 only one step process, just go through the transition state to give you the products in one step. So this occurs with the tertiary halide, generally reacts by this Sn1 mechanism, while the primary haloalkanes occurs by the Sn2 mechanism. So whereas these secondary, what about the secondary alkyl halide? They may react by Sn1 or Sn2 mechanism depending upon the nature of the solvent. So here I just want to compare some of the factors which are affecting the rate of Sn2 and Sn1 reactions, one of which is the structure of alkyl group. So Sn2, as I said, that in Sn2 it occurs in one step. So the order of reactivity of alkyl halide in Sn2 is first like your simple methyl, and then primary alkyl halide, then secondary undergoes, and tertiary. So like the compound which are just bulkier groups, or there is an steric effect on, like for example neopentyl, these primary halides are go through these Sn2 mechanism. So one important factor behind this order of reactivity is steric effect. So steric effect is the steric hindrance due to the special arrangement of atoms or groups at the site of reacting molecule, which will hinder the entering of attacking nucleophile, like in case of this Sn1. So it blocks, and due to this steric or the effect or hindrance, this will hinder the entering of attacking nucleophile of the carbon having a leaving group. So compound. Mostly the methyl halides, means the primary alkyl halide, reacts more rapidly in Sn2, which do not interfere or hinder with the approaching nucleophile, whereas in tertiary alkyl halide, which hinders, and due to the presence of alkyl group, it goes through tertiary alkyl halides, go through the Sn1. It will prefer Sn1 mechanism because the carbonium ion form, so the tertiary carbonium ions form is more stable as compared to the secondary and then primary one. So it is because of the fact that alkyl groups are electron donating and will disperse the positive charge on the carbons, central carbon, and this tertiary carbonium ion, which is formed in case of this Sn1, is more stable than the secondary carbonium ion and then to the primary carbonium ion. Second factor which affects these rates of reaction is the nature of the leaving group. The best leaving groups are ions or molecules that are weaker bases. Just like in halogens, if you are going through the halogen, the iodine is the best leaving group and fluoride is the poorest in the halogen atoms, because the order of basicity is like fluoride is greater base is compared to chloride, bromide, and iodine. So the rate of reaction in Sn1 and Sn2 will be faster when the leaving group is weaker base. One more factor, which is the nature of the nucleophile reagent, which affect the rate of Sn1 reactions and Sn2. So Sn1 rates are unaffected by the nature of the nucleophile because only one species is involved in the rate determining step. So it is unaffected by the nature of nucleophile because it is simply attached and already formed carbonium ion. It depends once the carbonium ion is formed. So strong these type of nucleophile which pushes the halogen from the molecule in Sn2 reaction favors it. So strong nucleophile is that which reacts rapidly with the given substrate. So like OH is a strong nucleophile and its conjugate acid like water, similarly then its conjugate acid water. Similarly, RO, which is alkoxy, is stronger than your alcohol. So concentration of nucleophile also affect these rates. The higher the concentration of your nucleophile, it will favor the Sn2 mechanism. Whereas lower the concentration of nucleophile, it will favor the Sn1. One last factor, which is the nature of the solvent. As I told you, the poor solvent, or we may call it the non-polar solvent, favors the Sn2 mechanism, while the polar solvent favors the Sn1 mechanism. The polar solvent, due to their high dielectric constant, help in separation of charges, so that in first step we have to make the carbonium ion. So polar solvents are more effective in solvating the ions in the Sn1 reaction by forming the hydrogen bonds or so on. So it will favor Sn1 reaction. While in the rate of Sn2 also increases in polar solvent, while the nucleophile is neutral molecule. And on the contrary, the rate of Sn2 decreases in polar solvent If nucleophile is negatively charged and electrical charge is dispersed in the transition, increases the transition. Increases the energy of the activation in the transition state. So polar solvent most commonly favor Sn1, while non-polar solvents favor Sn2, and these favors the tertiary alkyl halides goes through the Sn1 mechanism and primary through the Sn2. What about the secondary alkyl halides? Secondary alkyl halides will gives you the both type of reaction, Sn1 and Sn2 mechanism. It will go through. Depends upon the nature of the solvent. If the solvent there is a polar solvent, it will go through Sn1, and if there is a non-polar solvent, so it will go through the Sn2 mechanism. That's all about the substitution reaction of